Okay, so I'm going to go over this last little bit with respect to NMR in this video. So hopefully you guys are watching this and you're actually paying attention. So we had talked already about each shape or each signal in the NMR spectrum having a couple of different characteristics, right? So the first one that we talked about was the chemical shift. So chemical shift, we can abbreviate as delta. This had to do with the overall magnetic field that each various proton felt, right? And this had to do with inductive effects, as well as that diamagnetic anisotropy, right? So the presence of pi bonds, etc. Okay, so that was going to give us an idea of where the proton was at, what type of electronic environment, was it near electronegative atoms, etc. Okay, the second characteristic that we talked about was the integration, and again, this was the area under the curve, right? And so this was going to give us some indication of the actual number of protons that were giving rise to the signal, right? So we can integrate under every signal and essentially know how many protons are responsible for creating that signal, which is very, very helpful, okay? So this last one, or this last characteristic of each signal in the NMR spectra is something called multiplicity, or what we're going to also call spin-spin coupling or spin-spin splitting, right? And this is going to have to do with the overall shape of our signal, right? So this is probably the most important information that we can come away from with respect to an NMR signal, because what this is going to do is it's going to tell us about the other protons that are nearby our proton in our signal, okay? And hopefully I can explain what I mean by that. But this is going to give us a good indication of who is nearby each proton that we're dealing with in our NMR spectrum, so that we can essentially piece together the overall structure of the molecule, okay? All right, so first off, let's talk about what I mean by shape. And so with respect to shape, I've been alluding to, when we've been looking at our little NMR spectrums, I've been alluding to the fact that sometimes signals will look like just one peak, right? But sometimes I've been calling signals that have, let's say, 2 peaks or even 3 peaks. I've also been calling these guys individual signals, right? And so when we're talking about shape, is if this is a signal and this is giving rise or coming from one set of non-equivalent protons, then why don't we see a single peak for all of them, right? Why in some signals are we seeing 2 peaks, in some signals we're seeing 3 peaks, and so on, okay? So before we get started on that, I want to talk about or define what we actually call these various numbers of peaks, right? So if we do have only one peak for a signal, this is something that we call a singlet. If we have a signal, though, that is split into 2 peaks, so 2 different peaks, and these guys were of equal height, then we call that a doublet. If we have 3 peaks where we have a 1:2:1 ratio, we call that a triplet, and so on. Okay, so I'm going to utilize these words, quartet, quintet, sextet, septet, as I move through this. So just note, if I refer to a quartet, I'm referring to a signal that has 4 peaks, and they integrate into a 1:4:4 ratio, I think. Yeah, but just note, that's what I'm meaning by quartet, quintet, sextet, septet, etc. Okay? All right, so now the question is, what is going to take a signal in the NMR spectrum and turn it into something like a doublet or a triplet, etc.? All right, so now, what is the actual basis behind all of this? So now let's imagine that we have a molecule, and we are really, really, really interested in looking at the signal for HA, so proton A in this overall molecule. Okay, so we're interested in the signal for this guy. Okay, and again, its chemical shift is going to be determined by the types of atoms, electronegative atoms that it's around, also by the pi electron that it's around, etc. So that's going to be, determined in terms of chemical shift. Okay, now let's imagine that we're, doing our little NMR, and we've got our magnet, and it's being applied to HA, and we know that HA is going to split into its alpha or beta spin states, right? And that difference in energy is going to essentially determine the chemical shift, right? Now, we also have to understand that HA, especially in this particular compound, is nearby HB. And what's really important to note here is that HA and HB are non-equivalent. So these are different protons. Okay, they are not equivalent to one another. Okay, so HA, HB. All right, we're still interested in looking at the signal of HA, right? But we've applied our magnetic field now, and we know that HB has its own little magnetic field itself, right? So when we apply that magnetic field, HB can either be, let's say, the alpha spin state, right? So we can either have its magnetic field in line with the magnetic field that we've applied, or it could have a beta spin state. It can be against and opposing the field that we've applied. So this would be our alpha, and this will be our beta, right? And the minute we apply that magnetic field, HB is going to take on one of those two states, alpha or beta, okay? Okay, so now let's say in one molecule, HB takes on the alpha spin state. So in one molecule that we're looking at in the sample, HB is alpha, okay? Now, that is its own little magnetic field, right? That is its own little magnet. It's its own little magnetic field. And because of that, HA is going to feel that tiny little magnetic field that HB has now taken on, okay? And so because of that, because again, we have this external magnetic field, we have all these other factors that are affecting the overall signal of HA, this guy being in line with our external magnetic field is also going to affect HA, okay? So for this molecule, because HB, who's right nearby, has a little magnetic moment, HA is going to feel that little magnetic moment, and it's going to have its signal split a little bit larger comparatively to if HB wasn't there, right? So we have a molecule, we're looking at the signal for HA, HB has aligned with that field, and so HA feels that, and its signal between alpha and beta is split just a little bit more, because it's feeling a little bit more of that magnetic field, okay? So that's one molecule, okay? In another molecule, on the other hand, when we apply our external magnetic field, let's say HB actually takes on the beta spin state, right? So for this guy, because HB took on that beta spin state, HA feels the presence of that beta spin state, right? Feels that opposing magnetic field. And because of that, HA doesn't feel as strong as a magnetic field, right? So its alpha beta spin state energy is going to be a little bit smaller comparatively, okay? So these are the two possible outcomes. HA is either near an HB that is aligned with the field, or it's near an HB that is aligned against the field. And so because of that, instead of getting just one signal, one peak out, we're going to get instead that peak split into two, right? We're going to get that peak split into slightly higher downfield and slightly lower downfield, right? So we'll be at one guy where we have a little bit higher of an energy state, and we'll get one guy that has a little bit tiny lower of an energy state. And so because of this, we get what is called a doublet, because there are two possible outcomes. HB, who's nearby HA, is either with the field. If it's with the field, we get a little bit larger splitting, right? And so we get a little bit higher of a chemical shift. If we're near an HB that's aligned against the field, then we get a little bit smaller of a splitting, and we will absorb at a little bit lower of a chemical shift, right? And so the big thing to note about this is the fact that HB, 50% of the time, is going to align against, and 50% of the time is going to align with. So this is an equal probability, and that's why the two peaks here are equal in magnitude. This is what we get when we get a doublet, okay? Okay, so just note that here, HA, who we're interested in, this is his signal that is being split, was nearby only one non-equivalent proton. And when we were nearby only one non-equivalent proton, we end up getting two peaks as a result. And again, that two peaks is called a doublet. Okay, so what's next? All right, so that was HA. Nearby only one non-equivalent proton, right? What if we had HA, again, the one that we're actually interested, what if in a different molecule it was nearby HB, right? But now it was nearby two non-equivalent HBs, okay? So again, these two, HB is non-equivalent and different than HA, but these two guys are equivalent with respect to one another. Okay, so these guys are equivalent protons, all right? Okay, so similar thing. We're interested in the signal for HA, and we're interested in the signal for HA in the presence of these two non-equivalent protons, HB. Okay, now same exact thing that we were talking about before. When we apply our magnetic field, right, there's a couple of different outcomes for what HB is going to do that's going to affect HA, right? So, for example, let's say we apply our magnetic field. Get rid of this guy. And when we apply that magnetic field, we find in one molecule that this HB aligns in the alpha spin state, and this HB also aligns in the alpha spin state, right? So in one of the molecules, HB, both of the HBs are aligned alpha, right? And so because of that, HA is going to feel both of those magnetic fields, and it's going to be split. Its alpha beta spin state is going to be split a lot more if they weren't there, okay, comparatively. Not a lot more, but more than if they weren't there, okay? So that's one possible outcome. In another molecule, let's say HB, we'll call this HB1, we'll call this HB2. Let's say HB1 aligns with, right, so with the external magnetic field. But in HB2, we actually see this guy in the beta spin state, and so it aligns against, right? So because of that, for this situation where we have one that is with, one that is against, we'll have a little bit lower of an energy spacing because we'll have a little bit smaller of that external magnetic field between alpha and beta, okay? All right, so then in another scenario, let's say that H1 aligns against in the beta state, but then HB2 aligns with in the alpha state, right? So again, this is a different, a different arrangement of these two different spin states, but the overall effect is going to be one against and one with, and so we're going to get the exact same energy splitting in that situation between alpha and beta. Again, we're looking at HA. This is HA's alpha beta that we're looking at, okay? And then finally, let's say that in the last molecule that we look at, we actually find that both HBs, HB2 and HB1, are both aligned beta, all right? So they're both opposing the external magnetic field, and so because of that, we will get a smaller, comparatively, splitting of the two spin states for HA, and we'll get a little bit, or we'll get absorbance at a little bit lower of a frequency, okay? So now in this situation, we had one of these guys where we had both HBs with. We had two different situations where we had one with, one against, and then we had one situation where we had both of the two HBs against, okay? And so what this turns into, instead of, again, one big signal, is we get a signal where we have a 1 to 2 to 1 ratio that's representing, again, let me try to illustrate this. This guy is representing this one, whereas both of these two, both of these two, this guy and this guy are representing the one with and one against, and that's represented in the big 1 to 2 to 1 ratio. And then finally, this guy is represented by this guy, right? So because there were two ways that we could arrange both of those protons for HB as one with and one against, we'll get a large peak right here in the middle. That's twice the size of the two peaks on the outside. Okay, and so this overall is what we call a triplet. This is a triplet. And again, a triplet, we're looking at 3 peaks, and they have to have that 1 to 2 to 1 ratio. Okay, so for this guy, we had HA, and this is HA's signal that will be split into a triplet. It was nearby 2 protons, right? So when we have 2 nearby non-equivalent protons, we end up getting 3 peaks. And again, they're going to be split in that 1 to 2 to 1 ratio. And then finally, if we consider what happens when, again, we are looking at HA, and we are looking at it in terms of 3 different HBs. Again, these 3 HBs are equivalent with respect to one another, but they're non-equivalent with respect to HA. If we went through all of the different combinations of how its spin state could affect HA, what we would find is we would find one situation where all 3 of them could be against the field. We would have one situation where 1 would be with the field and 2 against the field. And we would have 3 situations where 2 would be with the field, 1 would be against. And then we would only have one situation where both or all three of those little magnetic moments would be with the field, right? So if there were three nearby non-equivalent protons, we would end up with a signal that would have 1 to 3 to 3 to 1, right? Because again, if we went through all the different combinations, we would get 3 combinations where 1 would be against, or 1 would be with, 2 would be against. We'd get 3 different combinations where 2 would be with, 1 would be against. And there would only be one way that we could arrange them where we'd have all of them with or all of them against. So 3 nearby neighbors ends up with a signal that has 4 peaks, and that 4 peaks is what we call a quartet. Okay, so hopefully I've been trying to allude to this pattern that we're getting out to the side. But at the end of the day, if we had one nearby neighbor, we got 2, we had 2, we got 3, we got 3, we got 4. The number of peaks for a given signal is going to follow what we call the n plus 1 rule, where n is the number of nearby non-equivalent protons. I'm going to define what I mean by nearby in a second. Non-equivalent, let's just write this well. Non-equivalent protons. Okay, so nearby non-equivalent protons. If we want to know how many peaks our signal is going to be split into, we need to count the number of nearby non-equivalent protons, and then we need to add 1 to it, okay? Okay, so a couple of things to note. This n plus 1 rule, or this splitting, or what we're going to call this multiplicity, has a couple names. It's something that's called spin coupling. So these protons couple together. That's why we get this overall effect. It's also called spin splitting, because the overall effect, or what we see in the NMR spectrum, is the actual splitting of the signal. Now, a couple important things to note about it. You're only going to see this spin coupling, spin splitting when the protons are non-equivalent with respect to one another. If you have equivalent protons are not going to split each other. You're only going to get one signal from equivalent protons. Okay, so it's only going to occur. We're only going to see this splitting pattern when we're dealing with non-equivalent protons that are nearby. Okay, number 2, what do I mean by nearby? So I'll say nearby or neighbor protons. What we mean by that is that you're only going to see splitting between protons that are 2 to 3 sigma bonds away. That's a big characteristic thing that you need to know, okay? So for example, let's say that I had a molecule here where I had a proton A, let's say, and it was nearby proton B. And again, the most important thing with respect to this is that these are non-equivalent. So these are non-equivalent, okay? Now, A with respect to B is only 2 sigma bonds away, so we would see splitting here. There would be a splitting pattern, okay? This is what we would call geminal protons as well, because they're on the same carbon, so they're Gemini, they're twins, they come from the same carbon. Okay, another situation where you would see splitting is if we had something like HA here, and it was nearby HB here. Okay, so these again are non-equivalent. We're looking at whether or not they're going to actually split each other. They're going to couple with each other. If we count the number of sigma bonds between HA and C, we have 1, we've got 2, we've got 3. So this we would also see splitting. So for both of these situations, you would see splitting. Okay, now a situation where you wouldn't see splitting is where you have HA and HB is way over here. Okay, so if we count the number of sigma bonds, we've got 1, 2, 3, 4. So because this is 4 sigma bonds away, you will not see splitting here. So this is no splitting in situations like these, okay? Or 5 or 6 or however many far apart they are, okay? Okay, so spin coupling, spin splitting, it's only going to occur when we are 2 to 3 sigma bonds away from each other. And then also, I do give you the list of the multiplicity of the peaks, so doublets, triplets, quartets, and the actual integration of the different components of each signal, right? So in the triplet, it was a 1 to 2 to 1 ratio. In a quartet, that was 1 to 3 to 3 to 1. We didn't go over what happens when there are 4 or 5 or 6 neighboring protons, but just note that it follows a kind of general pattern. I forget what this is, if this is like Pascal's triangle or something. I think it is. There's like a mathematical pattern that it eventually follows that I don't know, obviously, at this point in time. But just note, you're looking for quintet, you're looking for like a peak nearby a peak that's bigger than it, nearby a central peak, and then they go back out, right? So I'll show you what I mean by all of these in a second. Okay, so now we're going to do an example, and then we're going to go through a practice problem. So in this example, we want to determine the multiplicity for each signal in the following molecule. Okay, so again, the first step in doing any of this is determining the number of signals in the molecule. All right, so I'm going to start off on our left over here. And for NMR, for H1 NMR, proton NMR, we are looking for protons, right? And so again, with all of our bond line structures, we never draw the protons on. So I'm going to start out here at the left. I'm going to note that out on the end here, I have a methyl group, right? So this is a methyl group. And we already know that all methyl protons are equivalent with respect to one another. Right, so these guys are all going to be equivalent. But we should also note in this isopropyl group, they're also equivalent with these guys, right? Because this bond can rotate. If it rotated, we wouldn't be able to tell the difference between the two. They're in the exact same chemical environment, so all of these guys are equivalent. And we'll call this signal HA. So we'll call this HA. And all these guys can be little a's, etc. Okay? Okay, so then if these guys are all equivalent to one another, we move on. We'll note that there is a proton right here at this carbon. It is non-equivalent to the HAs, obviously. They're in very different electronic environments. It is by itself. We would call this a methine proton. And so we will call this guy HB. So that's our second signal. As we move on to the next carbon, there are no protons here, so we can ignore that. We'll move on to the next carbon. We note that there are 2 implied protons here. There is no chiral center in this molecule, right? So both of these protons are equivalent to one another. So we can go ahead and highlight them. These guys are equivalent to one another. We'll call them HC. As we move on, we've got 2 more protons out here. They are different from HC, right? HC was right near a carbon that had an oxygen on it. This is now, that was alpha. This is now beta to that. So HC is not equivalent to these new protons. We'll call these guys HD. So these are unique. They're not equivalent to HC. They're HD. As we move out, we can note this carbon has no protons on it. It's attached to entire methyl groups. And overall, this group on the end is called a tert-butyl group. So all of these guys end as methyl groups, right? So they all have protons. And most importantly, on them, all of these guys are equivalent with respect to one another, right? So all of these guys in this tert-butyl group, these guys are all equivalent protons, okay? So we're at A, B, C, D. We'll call these guys H, E. So this will be our HE signal. Okay, so that's number 1. We have to figure out how many signals we're actually going to see. Number 2, now we can worry about the multiplicity of each. Okay, so we're going to start over here with HA. So HA, in considering its multiplicity, so note that each H here, these guys are all equivalent protons. They're not going to split one another, right? So we're only concerned with the number of protons that are 2 to 3 sigma bonds from HA. Okay, so if I started, let's say, out here on this HA, so this guy, and I counted 1 in, and I counted 1 over, so that's 1, 2, and I counted this guy, this is 3. This is the only proton, HB is the only proton that is within 2 to 3 sigma bonds from all of these HAs, okay? So because of that, the only thing that is going to split this signal for HA is just HB, okay? And again, we're going to follow that n+1 rule, where n is the number of nearby non-equivalent protons. That is only satisfied by this guy. We're 3 sigma bonds away. So for this, we would have only 1 + 1, which gives us 2. And so this entire signal for HA would be split into a doublet, 2 peaks. Okay, and what's important to note is that if you actually saw it, right, we would have a doublet for HA, and it would have an integral of 6 protons, right? Because again, this signal has 6 protons that are making it up, right? It is being split by only 1. That's why we see the doublet, the multiplicity pattern that we do, okay? Okay, so now we'll move on to HB. So HB is just this one little guy by himself, right? But if we're looking for the number of nearby non-equivalent protons, HB we just counted was 1 to 2 to 3 away from HA, right? And when we count this, we count all of the HAs, right? So it's not just this guy, it's also this guy and this guy and this guy and this guy and this guy, okay? If we went the other way for HB, trying to look for other protons that it would couple with, if we went 1, 2, 3, 4, HC is too far away from HB to couple with it. Okay, so we won't actually get any coupling over here. And so HB will only couple with HA. And again, if we're following the n+1 rule, there are 1, 2, 3, 4, 5, 6 HAs that HB will couple with. And so this is 6 + 1, which gives us our 7, right? So HB overall would have a signal that is split into 7 separate peaks. This is called a septet. And a septet would have a 1 to something to something to something to something to something to something ratio, right? So it's 3 little tiny peaks raising to a peak, and then we move back out. We have 1, 2, 3, 4, 5, 6, 7 different peaks, right? Now, what's important to note here is that in the actual signal, in the actual NMR spectrum for this guy, this would have 7 peaks, but when we integrated it, it would only integrate to 1 proton, right? Because there's only 1 proton that's actually giving rise to the signal. That signal is being split into 7 separate peaks. Okay, so then we'll move on to HC. Move this guy out here. So HC, again, we're looking for protons that are 2 to 3 sigma bonds. We know already that HC back to HB was 4 sigma bonds away, so we don't even consider anything on the left-hand side. Again, they don't split each other, so we don't have to consider that, but they are going to be split by, if I get a red here, we've got 1, 2, 3. So they will be split by HD. And HD only, right? And so it's going to be both of the HDs. So for HC, if we're following the n+1 rule, there are 1, 2 HDs. 2 + 1 is 3. So this would give us our triplet. And when we actually saw the peak for that, it would be a 1 to 2 to 1 ratio. And again, this would integrate into 2 protons. Integration would be 2 protons, giving rise to this HC signal. Same thing for HD, right? So for HD, we have 1, 2, 3. So HC is going to be split by HC. If we go the opposite way, though, 1, 2, 3, 4, we're not going to be split by HE, right? So we're only going to see splitting from HC. Again, there's 1, 2 HCs, so n+1, 2 + 1 equals 3. So HD would also be a triplet. And it would also be a 1 to 2 to 1 ratio, and it would integrate into 2 protons. And then finally, HE. So HE, there's a bunch of them, right? There ends up being 1, 2, 3, 4, 5, 6, 7, 8, 9 different protons. They don't split each other because they're all equivalent, right? And if we go back for HE, we find 1, 2, 3, 4. Right, so the nearest proton that could split it is 4 sigma bonds away. So because of that, for HE, n+1, n here is 0. There are no protons nearby that can split this, so 0 + 1 gives us a 1. So we're going to find that all of these guys are just going to be a singlet. One single peak, and that one single peak is going to integrate into 9 protons. Okay, so go ahead and try these below. I want you to determine the multiplicity for each signal in these 2 molecules. You'll find some patterns here that will emerge long term. Hopefully they'll start to emerge quickly so that you can easily see the type of signals given the type of structure in a molecule. Okay, so we'll start over here with the first one on this guy. So we'll start out left. We do have protons out here. These are methyl protons, so these guys are all going to be equivalent with respect to one another. And again, we'll call this signal HA. As we move in, at the next carbon, there's no protons. At this carbon, there are protons. There are 2. So we'll call these guys, there's no chiral center in the molecule, so that's nice. We'll call these guys HB. So BHB. There's an oxygen, and then we move on to 2 more protons. Again, they are different from the original HB, and they are equivalent with respect to one another. So we'll call these guys HC. And then as we move out to the end, we have a methyl group. There's no axis of symmetry in this molecule. There's no plane of symmetry. And so these guys will all be equivalent to one another. And we'll call them HD. Let's go ahead and write over that again. Okay, so now multiplicity for each signal. All right, we're going to start with HA. So HA, again, for multiplicity, so I usually abbreviate this M, we're looking for nearby protons that are non-equivalent, that are within 2 to 3 sigma bonds away. So if we start by counting in, we have 1 sigma bond, we've got 2 sigma bonds, we've got 3 sigma bonds, and then we've got, at the very end here, 4 sigma bonds, okay? So because the closest nearby neighbor protons are 4 sigma bonds away, there will be no splitting with HB. They will not couple with one another. So there's no splitting there, like I just said. And because equivalent protons, all these HAs don't split one another. If we go to our n+1 rule, HA n+1, they're 0 plus 1. So we're going to get a peak of 1 or a singlet. Okay, so next we move on to HB. So HB we know is not going to be coupled by HA because we've already counted 1 to 2 to 3 to 4. So we're not going to get any splitting on this side. If we go the other way, we go 1 to 2 to 3 to 4. We're also not going to see splitting. So here for HB, we have n+1, so 0 plus 1. We're also going to get a singlet. So then as we move out to HC, HC is nearby somebody. We have 1, 2, 3. So HC will be split by HD. There's 1, 2, 3 HDs. So for HC, we've got 3 plus 1, which gives us 4. This is a quartet. And then finally for HD, we know HD will get split 1, 2, 3. Will get split by HC. There's 1, 2 HCs. So for HD, in terms of multiplicity, we get 2 plus 1, which gives us a triplet. Okay, so moving over, that's first molecule. Now we'll go on to B. So similar thing, we've got 3 protons out on the end here. This is a methyl group, so they're all equivalent with respect to one another. There is no protons here. There's 1 proton here. There are 3 protons here. There are 2 protons here. There are no protons here. And then there are 9 protons out on this terbutyl group, out on this terminal terbutyl group. I'll go ahead and just draw those in. 1, 2, 3. Okay, so that is the signals. So now let's talk about the splitting pattern that we could expect. We'll start out to the left. So these guys we'll call HA. They're not going to split one another. And then if we look for nearby neighbors, we've got 1, 2, 3, 4 would be the next nearby neighbor. So because of that, this methyl group, HA, is isolated. And we would expect a 0 plus 1, which would give us a singlet. So these guys are a singlet. As we move on, we'll go to this guy next. So this is a methine proton. It's by itself. But now there's something that's different that's going to happen here, right? So comparatively, if we count in, we've got 1. So we've got 1, 2, 3. So it's 3 bonds from, what do we call these guys? So I guess if this was, I guess if we call this guy HB, these guys would be HCs. Okay, so we're 3 bonds from HB to HC. We're also 1, 2, 3 bonds to what we'll call HD. Okay, so HB is going to have kind of a complex signal. We'll talk about this in a second. In general, though, you're going to count these guys as the same, that they're going to have the same overall effect. So we've got 1, 2, 3, 4, 5 that are going to split HB. So this is 5 plus 1, which gives us 6. So this is a sextet. That's HB. If we move on to HC, so HC is only going to be, we've got 1, 2, 3. It's only going to be split by this one HB, right? So we have 1 plus 1, which gives us 2. HC is going to be a doublet. And then same thing for HD. If we move HD up here, right? So HD, if we count, we've got 1, 2, 3. If we go the other way, 1, 2, 3, 4, doesn't count. So HD will also just be 1 plus 1, which is 2, which is a doublet. And then finally, as we get out here, all of these tert-butyl protons, all of these guys, we'll call these HE. We already counted, trying to count in for HD, so this was 1, 2, 3, 4. So there is nobody that's going to split HE. So because of that, all 9 of those protons would be 1 peak. They would be a singlet. Okay. All right. Hopefully that is clear with respect to actual problems. We're going to show in a second what happened here with HB, how sometimes this can get obscured a little bit because it was being split by 2 different sets of non-equivalent protons. Then after that, we'll move into how we can actually utilize this. Okay, so we're going to cover a couple just kind of cleanup topics just to finish out this idea behind coupling. All right, so when you have protons that are coupling in a molecule, they're going to have what we call a coupling constant, or another word for that is a J value, okay? And it's essentially going to be a measure of how much their interaction is actually splitting the signal or splitting the overall peaks, okay? So for example, if we have an ethyl group here where we have HAs are equivalent, and we also have HBs. HBs are equivalent, they're both splitting each other. HA and HB are going to share a coupling constant, right? And we call that, or we abbreviate that J, and because it's between these 2 protons, we'll call this JAB. It's the coupling constant between the HAs and the HBs, okay? All right, so if we were looking at the splitting pattern that we would expect here, HA, which is a methylene group, is being split by 1, 2, 3 protons in HB. So 3 plus 1 gives us 4. This is a quartet. So for HA, we're going to expect a quartet, right, which is what we get at whatever part per million. And then for HB is being split by A. There are only 2 A's, so 2 plus 1 is 3. So for HB, we could expect a triplet. Okay, now where does this whole J value or this coupling constant come in? So this is our HA signal, this is our HB signal, right? So this J value is the actual measure of how far apart these peaks are, right? So this JAB, or this coupling constant, is going to define the distance between the peaks and the overall split pattern, right? So it's going to be the same for all of the splitting for each signal, okay? We're also going to find the exact same J value, exact same distance for the signal for HB as well, right? So this distance, right, between peaks is going to be the same for protons that are splitting one another, okay? So this distance is equal to this distance over here because HA and HB are interacting and they're sharing that exact same J value or coupling constant, okay? Okay, so how would you use that? Well, most of the peaks that you guys are going to see are going to have similar distances regardless, so it's not going to be necessarily useful. But if you had a signal, let's say, that had a really large splitting or a really large J value, and it was nearby something that had a very small J value, you could tell from the distance between these that these were not interacting with respect to one another, right? So if there was any question about whether or not this was giving or was interacting and splitting this, then because those distances are very, very, very different, you could tell, no, these guys are not actually splitting with respect to one another, right? Another thing to note is that these J values are measured in units of frequency, and they're going to be constant regardless of the operating frequency of the instrument that you use, right? So they're going to fall in between about 0 to about 20 hertz, depending on the protons. And again, this is not going to change if we use a higher operating frequency instrument, okay? So we use a stronger magnet. Now, what's the big point behind that? Well, this is why we like to use higher operating frequency instruments, because this J value is constant. Let's say, for example, we had a situation where the J value here was, let's say 7 hertz, right? If we were looking at that coupling in, let's say, a 60 megahertz instrument, so one of those really low end, very low operating frequency instruments, that J value ends up being about 1/10 of a delta unit, right? So let me write that, 1/10 of a delta unit. So because of that, these signals start to overlap with respect to one another, and so you can't make out the entire spectrum. If you were to take that exact same coupling constant and use, like, let's say a 300 megahertz instrument, then 7 hertz in a 300 megahertz instrument is only like, a 1% of a delta unit, right? So because of that, these signals actually get to be resolved, and they're not going to overlap with respect to one another. So this is one of those big things about why a higher operating frequency instrument is better. It's because in lower operating frequency instruments, these really high J values are going to overlap, and we're not going to be able to discern all of the signals because of that. So the higher the operating frequency, the less a fraction of a delta unit these J values take up, and so we can essentially look and see all of the various peaks in the spectrum, okay? Okay, so with respect to some of these different types of structures, we can find that certain groups are going to have very specific patterns in the NMR spectrum, right? So for example, if we were to draw out an ethyl group, so carbon, carbon, and we were to look at the different protons on an ethyl group, so let's say these guys are HA, and then these guys on the end, we'll call these HB. So HA and HB are non-equivalent with respect to one another, but they are equivalent with respect to each other. So HA, both of these guys are equivalent protons, whereas HB, all three of these guys are equivalent protons, right? So now an ethyl group is going to give a very characteristic pattern in the NMR spectrum. So for example, if we looked at HA HA is a methylene proton. They're methylene protons, so we could expect their chemical shifts at about 1.2 parts per million. Most importantly, though, with respect to the splitting, with respect to multiplicity, they're going to be split by HBs, which we have 1, 2, 3 HBs. So 3 plus 1 gives us 4. So we can expect a quartet for HA. Whereas for HB, these guys are methyl protons, so we expect them at about 0.9 parts per million. And they're going to be split by HA, of which there is only 1, 2 of it. So 2 plus 1 is 3. So we can expect a triplet for HB, right? So if we looked at the NMR spectrum, we could expect a triplet at about 0.9 parts per million, right? 1 to 1 to 3. That is upfield comparatively to a quartet, 1 to 2 to 1 to 2. This one needs to be a little higher, right? This guy would integrate into 3 protons, and this guy would integrate to 2, right? So a triplet slightly upfield of a quartet with those types of integration patterns is really indicative of an ethyl group in your molecule. Same thing for isopropyl. So if I draw isopropyl using bond line, it looks like the Y. If we drew it using a Lewis structure instead, we have a methyl group, and then a methine proton. And we can note that this methine proton is its own separate thing. It's not equivalent to the other protons here. But these guys, these 2 methyl protons, these guys are equivalent to each other, right? So these guys are equivalent, right? So they're going to give rise to one signal. Okay, so what would that signal look like? Well, for these guys, these are both methyl groups, so we can expect them at about 0.9 parts per million. And they're going to be split by only one other thing, this HA, because again, we're 1, 2, 3 sigma bonds away. So we could expect a 1 plus 1, a doublet for this guy. All right, so those are the methyl protons of the isopropyl group. On the other hand, if we looked at the methine proton, so for methine, we would expect a 1.7, a signal at 1.7 parts per million. But now this methine proton is going to be split by all 6 of these methyl protons here, right? So our splitting pattern for HA would be 6 plus 1, which is 7, right? So we could expect a really, really, really tiny septet that integrated to 1 proton, right? Which is what we see at about 1.7 parts per million. And that's going to be downfield of a doublet that integrates to 6 protons at about 0.9 parts per million, right? So tiny, tiny, tiny little septet that is downfield of a doublet is a really big indicator that you're dealing with an isopropyl group. And then finally, for tert-butyl, so tert-butyl, if you remember, is the chicken feet. When we're looking at tert-butyl, we're looking at the protons on the end, these methyl protons. And if I drew one of them on, for tert-butyl, we'll find that we're too far away to be split by anyone, right? So we're 1, we're 2, we're 3, and then the next closest proton that could split any of these guys would be 4 sigma bonds away, right? So because of that, there's no splitting. They don't split each other, right? And there are essentially 9 of them overall. So what we'd find in a tert-butyl is we'd find a signal that would be really, really, really large singlet that would integrate to 9 protons at about 0.9 parts per million. So if you ever find a signal in your spectrums that integrates to 9 protons, that's a really big indicator that you're dealing with a tert-butyl group. Okay, and so then finally, we kind of glanced over this before when I was talking about or doing that problem with expected splitting patterns. But let's say that we had a molecule, let's say something like this, where we have HB, right? So HB is a signal that we're really interested in this molecule, and it is being split by 2 different sets of non-equivalent protons, right? So HB right now is being split by the HCs, right? So we have HCs over here, and it's also being split by 1, 2, 3 by the HAs over here. Okay, so beforehand, when we were looking at predicting the splitting pattern for HB, I just said, well, count HC and HA as the same, and just add them up, right? So if we were to do that, we'd say 1, 2, 3, 4, 5, 6, or no, 5, pardon me. So HB would be have a multiplicity of 5 plus 1, which is 6, so we could expect a sextet. Okay, so now, the thing about this is not exactly necessarily true, okay? In reality, and you won't actually ever get into this until you get into like really high order NMR spectroscopy, but this assumption that we made isn't true because, again, it's going to depend on the coupling constant or the J value of the two different interacting sets of protons, right? So we have two different J values that we can look at here. We've got what we're going to call JBC, and then we've got what we are going to call JAB, okay? So now, the thing is, if JAB and JBC are equal, right, or at least fairly close to one another, then we can expect a sextet, right? We can expect that they're all going to interact the same way, and it's going to split the signal into 6 different peaks, right? Now, if on the other hand, JAB was much larger, let's say, than JBC, what we're going to expect is instead something different, okay? So now, JAB, this coupling between B and A, that's going to split B into a 1, 2, 3, 3 plus 1 into a quartet, okay? JBC, this guy, the interaction between B and C, B is interacting with C, there's only 2 C's, so this would split B into a triplet, right? So this is 2 plus 1, 3, okay? Now, if JAB is much larger than JBC, what we're going to find is what is called a quartet of triplets, okay? And so this quartet of triplets would look something like this, right? Where we have the triplets from the JBC, and overall there's a quartet of them, okay? So now that's if JAB, the coupling constant between A and B, is much larger than the coupling constant between B and C. If, on the other hand, JBC was much larger than the coupling constant between AB, instead of a quartet of triplets, we would expect a triplet of quartets, right? So this is a quartet of triplets. This, on the other hand, is a triplet of quartets. And you can actually see this in the NMR spectrum if these coupling constants are fairly different with respect to one another. Okay, so again, if AB was bigger, you would expect to be split into a quartet of triplets, where if BC is bigger, you expect to be split into a triplet of quartets. Okay, so what really happens, especially with a lot of these just like methyl and methylene type protons, is that they're fairly similar with respect to one another. So we can just count them as the same and expect a sextet instead. Also, sometimes what will really happen is we'll get this really ugly multiplet, right? So what I mean by multiplet is like a bunch of signals that you can't necessarily discern what their splitting pattern is. So yes, for our intents and purposes, we're going to assume, especially for a lot of these just plain methyl and methylene protons, that these guys are equal and we can just treat them all the same. We'll expect a sextet for HB, but just note that that's not always the case, and it does depend on the value of the coupling constant between the two different sets of non-equivalent protons. Okay, so then finally, there's 2 other little cases that I wanted to bring up, and I'm not going to explain why this is, why we actually see this. I'm just going to tell you what to expect. So we've been looking at splitting patterns, right? We've been looking at multiplicities. And I just want to mention at the end here that there are some protons that don't actually undergo any type of splitting or coupling, right? So a good example of that, or the first example that we introduce you to, is alcohol protons, right? So this molecule over here is ethanol, right? If we drew out ethanol, we have an O, an H, And then we've got 2 H's here. And then we've got 3 H's here. Right? So if we're just looking at, okay, what would we expect not knowing anything about alcohol protons not actually doing any splitting pattern, we would say, okay, well, HA here is 1, 2, 3 sigma bonds away from this proton that's on the alcohol, so you would expect it to be split by that, right? So you would expect HA to be split by HB. It would also be split by 1, 2, 3. We'll call these guys HCs, okay? And so because of that, you say 1, 2, 3, 4, it's going to be split into a quintet, right? Now, unfortunately, you would think that, and you would be wrong, because these protons on alcohols, so these guys, do not split any other signal. Okay, so just note that. They're not going to be split, and they will not split anybody else. Okay, so because of that, our HAs here, our HAs are only going to be split by the HCs over here. So we could expect this guy to be 3 plus 1, which is 4. So HA will be a quartet. And then HC we could expect to be 2 plus 1, a triplet. And then again, they would have their own chemical shift. So HA is alpha to an alcohol. Yeah, alpha to an alcohol, we added on 2.5. So this would be 1.2 plus 2.5. We could expect this about 3.7 parts per million. And then for HC, this is beta to an alcohol. So it's a methyl group, 0.9 plus 1/5 of 2.5. So 0.5 equals 1.4. And then I also said, well, alcohol protons, they end up being at about 2 to 5, depending. But again, the big signal for this is that it's not going to be split, so it's just going to be a singlet. All right, so if we look at this, we'll find, oh, here is a triplet, which we expected, that integrates to 3 protons at about 1.4-ish. That may be stretching it a little bit. Here we find a quartet, which is what we expected, that integrates to 2 protons at about 3.7-ish parts per million. And then this last one proton not being split a little bit above 2, so 2.3. This has to be the alcohol OH. Okay, so again, alcohols, what's the big takeaway? They don't split, so don't look for splitting patterns there. The other one that doesn't have any type of splitting pattern are aldehyde protons. So remember, the aldehyde group is a carbonyl with a proton on the end, right? It's this proton that will not be split or will not split anybody else, right? So for example, in this molecule, there are 2 protons here. We're 1, 2, 3 sigma bonds away. It doesn't matter. There's still no splitting between these 2. Another big key for aldehyde protons is they show up at around 10 parts per million, and they're probably going to be just by themselves with an integration of 1 with no splitting, so there's going to be a singlet. Okay, so just note that alcohol, aldehydes, they're not going to actually split your signals. Okay, so now what's next? Well, we're going to utilize everything, or put together everything that we've learned to draw the expected H1 NMR spectrum for a couple of different molecules. And then we're going to flip that around, and given a spectrum, we're going to draw the molecule, okay? All right, so a couple things to look at with respect to drawing an H1 NMR spectrum. First thing we need to consider is chemical shift, right? So we've talked about how we can predict chemical shifts depending on the electronegative atoms that are around it. We also need to predict the integration, right? And we also need to take into account the multiplicity. So each signal is going to have a chemical shift, it's going to have an integral, and it's going to have a shape or a multiplicity, okay? All right, so we're going to start out here. On the end, we've got these methyl protons. So H, H, H. They are right now alpha to a carbonyl group, right? So remember, alpha to carbonyl, we're going to add 1 part per million. So for these guys, we'll call these A. For chemical shift, it's a methyl, so 0.9. but again, it is alpha to a carbonyl group, so we end up with 1.9 part per million. So we look at the integration here. There's 1, 2, 3 of them, so we can expect this to be an integral of 3. And then finally, for multiplicity, we are 1, 2, 3, very, very, very far away, right? So we're not going to see any splitting pattern here. So because of that, we are 0 plus 1, or a singlet. Okay, so now we'll move over. There's no protons here. No protons here. We do get a proton here. Right, so this is our nice methine proton. So for this guy, we'll call this HB. HB, for chemical shift, it's methine, so we'll have 1.7 to begin with. Now it is alpha to an ester, right? So this is alpha to an ester. So to that, we're going to add on 3. So we end up with 4.7 parts per million. So that's that. For integration, there's only one of them, so this will integrate to 1 proton. And now this is that kind of special pattern that you can tell. This is a tert-butyl proton at the end. So for multiplicity, this guy's going to get split by all 3 of these guys. Not tert-butyl, this is isopropyl. All right, so these guys are all different. We'll call them C's. C's, C's, C's. HB is within 3 sigma bonds away from all the C's. So there are 6 C's. 6 plus 1 is 7. This is going to be that characteristic septet with an integral of 1. Okay, and then finally, so that's HB. Finally, we'll move on to HC. So these guys are all equivalent with respect to one another. So for HC, we'll start with chemical shift. They are all methyl groups. And now if that was alpha to an ester, they're beta to an ester. So we're going to add on 1/5 of that 3. So 1/5 of 0.6 is 0.6, or yeah, 1/5 of 3 is 0.6. So we add those together, we get 1.5 parts per million. And then for integration, there are 6 of them, so there'll be 6 protons. And then for multiplicity, they're all equivalent to one another, so they're not going to split each other. They're only going to be split by HB, right? So we have 1 plus 1. This is that characteristic doublet that has an integral of 6, right? So now we're going to draw this. We're going to attempt to draw this. We're going to start with the farthest upfield signal, which is our doublet at 1.5. So I'm going to go ahead and put 1.5 here. I'm going to draw a doublet as best I can. I'm going to move down to the next in line, which is a singlet at 1.9. So we'll draw 1.9 here. Draw a singlet there. And then as we move out, the last signal we have is this 4.7. So we can move on down. May not be the best estimate here of where 4.7 is, but here we're going to draw a septet. So I'm going to go ahead and just connect this guy. We've got 1 to 2 to 3 to 10. Okay. And so again, to kind of illustrate this, we want to put the integrals on. So this is 1, 2, 3, 4, 5, 6, 7. Good. This is integrating to 1 proton. This is integrating to 3 protons. And this is integrating to 6 protons, right? So the integral values don't necessarily have to be like the most obvious, that the peaks, that the peak height is trying to indicate those. But you should try to draw kind of a good signal. This doublet's kind of ugly. I've been inspired by my septet, so I'm going to go ahead and just be a little bit more precise. Okay, so for each NMR spectrum, each signal is going to have a chemical shift that you should be able to predict. It's going to have an integral that you should be able to predict, and it's going to have a splitting pattern that you should be able to predict. Okay, so now we're going to flip that, and instead of drawing the NMR spectrum, we're going to take a spectrum, we're going to take the chemical formula for the molecule, and we're going to try to reconstruct what the molecule actually looks like. Because again, this is the purpose of NMR spectroscopy. It's taking an NMR spectrum, taking the molecular formula, taking other little bits of information, and actually determining what the structure of the molecule is, okay? Okay, so now in doing this, we're going to utilize this guy where we have the C9H10O, and it's given proton NMR spectrum as our example. I'm going to walk you through how I go about trying to piece these things together, okay? So there are going to be a couple of steps that you guys are supposed to follow in taking an NMR and taking a chemical formula and reconstructing the structure for it. The first step I tell you to do is determine the HDI. So you may think to yourself, well, what's an HDI? I haven't actually defined that, so we're going to define that first. The second, you're going to analyze the integrals, specifically the integral values here with respect to the actual chemical formula, and look for symmetry. You're then going to try to make fragments out of the various multiplicities and the integral values that we've been given, and then you're going to try to assemble those fragments into the overall structure. Okay, so again, I'm going to hopefully illustrate that as I go through this example. Okay, so the first step in determining the structure given the proton NMR is determining the what is called the HDI, or the hydrogen deficiency index, right? So what we're looking for here is degrees of saturation or unsaturation in a molecule. So what I mean by unsaturation, it usually tells us whether or not we have a double bond or let's say a ring in a molecule, because what it's looking for is, if you have this many carbons, if everything was perfectly saturated, how many hydrogens should you have, right? And so that's what we're essentially calculating. How many hydrogens are we lacking given that we have a certain amount of carbons, okay? So I'm not going to go into like all the various aspects of this. I'm mainly just going to define it. And so to calculate the HDI, what you're going to do is you're going to multiply 2 times the number of carbons in the molecule. You're going to add 2 to it, and then if there are any nitrogens, you're going to add them in as well. You're then going to subtract the hydrogens, and you're going to subtract the halogens. So this thing at the end is halogens, if there are any halogens in the molecule. Okay, so this is again the number. With that, all of these things in the parentheses, you're then going to divide that by 2. Okay, and if you get an HCI that's equal to 0, then the molecule is fully saturated, meaning there are no double bonds, there's no rings. If you get an HCI of 1, that's going to tell you that there is either a double bond or a ring. And then if you get an HCI of 2, there's a lot of different permutations of HCIs of 2, right? That could be 2 double bonds, that could be a triple bond, it could be 2 rings, or a ring and a double bond. So the higher the value of HCI, the less information we're actually going to get from calculating the HCI. So hopefully, if you're calculating HCI, you're going to end up with an HCI of 1, maybe an HCI of 2. The only other helpful one is that if you get an HCI that's greater than 4, this usually indicates the presence of an aromatic ring. And so HCI of 4 coupled with some other things is usually going to indicate the presence of this guy. Greater than 4, pardon me. Okay, so let's go ahead and calculate the HCI for this guy. All right, so we have carbon 9H10O. So for HDI, we're going to take 1/2, 2 times the number of carbons. So number of carbons here is 9, plus 2, and then we're going to subtract from it the number of hydrogens, right? So number of hydrogens is 10. This is number of carbons. All the other stuff in that formula was like nitrogen. We don't have nitrogen here. It was the halogens. We don't have any halogens in here. So this is really all we need to account for, is the number of carbons and the number of hydrogens. So when we do this, we get 1/2. 2 times 9 is 18, plus 2, which is 20. 20 minus 10 gives us 1/2 of 10, which gives us 5. So we have an HDI right now of 5. And again, I said, well, that's not very helpful, except if we have an HDI that is greater than 4. That's really indicative that we have an aromatic ring present. And so because of that, we're going to assume that there's probably an aromatic ring in this molecule, okay? Number 2, with that, we're going to start to look at our chemical shifts in our proton NMR signal, and then also the integrals for them, right? So remember, these integrals can sometimes be given to you as actual values, or sometimes they're going to give you like the actual number, like, oh, 1 proton or 2 protons, etc. Here we have 4 different signals, right? And the first signal integrates to 10, the second to 54, the third to 21, and the fourth to 22. To take these values and make them into actual numbers of protons, we're going to divide all of them by the lowest number. So this is 10.2, this is 10.2, and then divided by 10.2. What we end up with is 1, so 1 proton for this signal. We end up with 5 protons for this signal. For this guy, we'll end up with 2 protons, and then for this guy, we'll also end up with 2 protons, okay? So what I mean by looking for symmetry now is when I add up all of these guys, I end up with 10 protons altogether, which is the exact number of protons that I have in my molecule, right? So if instead I had added these up and ended up with 10 and there had been, let's say, 20, then that would have been a big indicator that, oh, this molecule is symmetric, and so I need to take that into account, okay? We don't have to worry about that, though. We have 10 protons, and we only have 10 to get rid of here. So each proton is giving rise to one of these signals. Okay, so now we're going to look at the actual overall little bits that we have here. So a couple things to note. This thing right in the middle, so it's clear to me, but it probably isn't clear to you. Anytime you get, again, what I'm going to call a multiplet, where it's really unclear, like they're kind of, I mean, what is that, like a quartet, a quintet, we can't really tell, that hovers about 7 parts per million, that is another really big indicator that we have an aromatic ring. Okay, so this has to do with that diamagnetic anisotropy. We also already had a big indicator via our HCI of 5 that this is an aromatic ring, so that's going to be one of our little fragments, right? We have an aromatic ring. Now, the integral for the protons in the aromatic ring here is only 5, right? So this is 1, 2, 3, 4, 5. So this other bit, or this other carbon, must be bound to something else because there's not a proton here. Okay, so we know that 5 of our protons are going to be present on this ring because of this integral, because there are 5 of these guys, and that 6th position is going to go out to something else. Okay, so now another big helpful hint in what else could possibly be present in this molecule is this 1 proton out here at about 10 parts per million. All right, so if we go back to that diamagnetic anisotropy, we talked about how the aldehyde proton ends up about 10, and it's fairly indicative that there's an aldehyde proton, right? And again, another helpful hint here is the fact that this integrates to 1 proton, okay? So this is going to be another fragment, and what helps here too is that takes into account the oxygen, right? So we have a fragment now that has included an oxygen that we had to get rid of in our overall structure, so that's going to help out, okay? So now this is good. We have at this point in time accounted for 1, 2, 3, 4, 5, 6, 7 carbons, and we have 9 to get rid of, so there are 2 more. We've also accounted for 1, 2, 3, 4, 5, 6 hydrogens, and there are 10 to get rid of, so we have 4 more, and then we've accounted for the oxygen, so that guy's gone, okay? All right, so now if we come back down here, we have 2 triplets that integrate to 2, okay? So again, if I just looked at one of these guys, so let's say this triplet, right? So this guy has an integral of 2, meaning that I've got a carbon that has 2 protons on it. We'll call these HBs, okay, that are surrounded by n plus 1 equals 3, right? Because this is a triplet, we can see 1, 2, 3, right? So my overall splitting is 3, and I know that's n plus 1 equals to 3. So n has to be equal to 2, right? So whatever this guy is, it needs to be nearby 2 other non-equivalent protons, right? So we call this like HC and HC, right? Same thing for this guy. There are 2 protons, right, that need to be nearby 2 other non-equivalent protons, because again, n plus 1 for this signal is 3, so there have to be 2 nearby protons, okay? So because of that, I could propose that this fragment is a methylene group that's nearby another methylene group, right? So this little bit together could be the last little bit to my structure, right? So we'll call this HB, I think that's what I called it down here, HB, HC, HC, right? HC, which would probably be, we'll call this guy, is going to be near that aldehyde. So aldehydes have to end structures because hydrogen can't bind with anything else, right? So we knew that we had this aldehyde group. We knew it was going to be a terminal position. What am I doing? This guy. Yeah, so this guy has to be an aldehyde group, and we know it has to be terminal. So HC is probably this guy because of that. Again, aldehydes don't couple, so we don't have to worry about that. And then HB, on the other hand, would probably be the thing that's attached to the aromatic ring, right? Because being near a carbonyl would shift it about 2, 1, I don't know. I forget what there's a little. I'm going to have to go back and look at that. Hold on just a second. Yeah, so, yeah, I think HC is the farther one downfield. Because again, for these guys, these would be 1.2 originally, and then we would add on 1 to account for the carbonyl, whereas these guys off of the aromatic ring, that only like shifts it like to 0.2 or to maybe at the most like, I don't know, 2.5, right? So again, I'm going to stick with this is HC and this is HB. It's slightly farther upfield. All right, but now with that, we've got these fragments that we can piece together, right? We knew that the aldehyde had to terminate, so it had to be on the other end of this guy. So the only thing left to put on the end of this guy is this aromatic ring, right? So now, if we can put the pieces together, we're going to have our aromatic ring. This is going to branch out into an ethyl group, or I guess... No, wrong one. Let's try that again. Into, yeah, an ethyl group that terminates in an aldehyde. H, double bond oxygen. Okay, so now again, it's important to check to make sure you have everything together. So we do have our 1 oxygen, so that is off the table. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, which is what we had before. For hydrogens, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so maybe if I drew this better, it would look better. Hydrogen to this guy, to this guy. All right, and again, a good check after you put the pieces together is to go back, right, and say, okay, if this was my molecule, what would be the expected spectrum that I could produce from this? Okay. Okay, so now given that, I want you to go ahead and try this one on your own, right? So now this guy, again, I can already define, has this crazy multiplet down here at about 7, right? So this is what I would define as a multiplet. All the other signals are nice and clear, though. So we've got a triplet here. We've got a triplet here. And then we've got a singlet here. And the singlet's at about 2 parts per million. I've given you the integral values, and so I want you to try to determine the structure of the C8H10O molecule given the proton NMR spectrum.